As you can see, we have a train collision problem. This isn't the easiest problem, it's not the hardest problem, it's somewhere in the middle. And I'm sure you can read yourself. One thing I'll just note is that when I say ms, to the -1 just means m divided by s. You'll often see the exponent notation because people are lazy, they want to fit their thing on one line. Anyways, here's the question, and the first thing I'll note is just what is a good process for solving a physics question. This is the most important thing, because later on especially, what you'll see is that there are so many moving things going in all sorts of different directions. If you're not comfortable with the process, then you're just going to get lost somewhere halfway in the middle, because these questions are going to start taking 20-30 minutes, even if you're focusing the entire time. So here's the process we're going to use. The first thing is, no one likes text, okay? Draw a picture. If you don't have a picture, it's really hard to get an intuition for what should happen, because we see things moving all the time. If we have a picture, we can keep track of the variables, and we can also get a little bit of a hint as to what do you think should be moving in which direction. The next thing is, we want to state our assumptions and even variables if we make any new variables. The reason for this is that, especially if you're taking physics in a school setting, it's gonna be a lot easier for people to give you marks if they can follow along easily, here's exactly what they're doing. So we want to make it easy in general, but also in academic setting, for people to be able to give us the marks we want. It's for people to be able to understand our physics solutions. Next, we're going to create table of equations. It's really important. A lot of people, when they just see a physics question, they just start scrolling all over the page. It's not going to go well. We're going to have these questions later on where we have pulleys in one place, ramps in another place, springs, balls rolling. You cannot keep track of all that on a messy page. So we really want to create a table of equations. These 3 steps, they're basically just physics. Okay, this is the physics part of any physics problem. If you do this and you have a nice teacher, they will give you at least 50% of the marks just for doing this. It doesn't matter what the final answer you get is. I was in university, we used to get 75% of the marks just for doing these steps, because these are the physics. After this, we're just doing math. We're just rearranging, solving for variables, and it's not too important in terms of testing, do we understand physics, whether we can solve equations correctly. And that's why a lot of teachers, all of the teachers I had at least, they never really placed much importance to this last step. Finally, if you're doing physics problems as part of a math course, make sure you have a summary, just say, oh, okay, we figured out that the minimum acceleration in this case is 15 meters per second squared, whatever. So here's our process. Let's dive into it step by step. You'll see that this question gets a lot easier when you're following this process. So first of all, let's worry about these things, the physics. We don't have to worry about what the solution is at all, okay? Don't think about the solution, let's just go through these steps and start with our picture. So I'm gonna make sure that I have 2 trains, and I'll keep in mind in my picture that they're heading in different directions, and it says something about distances, so I'll make sure to label distances. So let's see here. Let's say this is train A. Here we are. Let's say this is train A. It's going in this direction with some velocity, let's call it VA. By the way, we're talking about meta tips, so I'm assuming you know what velocity is, you know the kinematics equations, and if you don't, then Khan Academy would be a good place to go. So that's train A. Over here we're gonna have train B. Make sure that it's going in the opposite direction. So we're gonna call this VB, the initial velocity here. Also, they told us a distance, so let's make sure that we specify a distance. So initially, they are some distance apart. Let's call this like the total distance, ST. I don't know why they use S for distance, they just do. And that's all the information we've been given. But now this is the part where we can use our intuition about like what's going on. So if you think about it, you have two trains coming in together, right? We know that one of these trains is going faster than the other, but they're both gonna slow down at the same rate. Intuitively, what that means is we're gonna have, some point, let's say like around here, where both trains have stopped, and we know that the point is not going to be in the middle. How do we know that? Well, if one train is, it's going at 100 kilometers an hour, it slows down at 10 kilometers every second, well, you can't have the train stop in under 10 seconds. If the other train is going 50 kilometers an hour, also decelerating at 10 kilometers a second, well, actually the units don't line up there, but it's gonna be a shorter interval that it's gonna stop in. So let's say this train VA, if we just remind ourselves, this is heading east at 50 meters a second. Okay, let's say this is east over here. We'll declare that to be positive. So this is the positive direction. Then this train is going to be going faster than this train, right? If this train is going faster than this train, it's decelerating at the same rate as this train, then we're going to have a longer distance that it takes to decelerate, which we'll call SA, because it's train A. Train B, it's going at the same speed, well, it's going at a different speed, but it's decelerating at the same rate. So it's going to decelerate more quickly. By the time the trains get to this point over here, both VA final and VB final are going to be equal to 0 because they both stopped. And this is what it means when it says they barely avoid colliding, which is like they just get to the point where they're like front ends, locomotives are just grazing. So this is why we made these assumptions, right? We assume that they're just going to get, almost touching, but then the velocity is just going to be equal to 0 when they get to this final point here. So now that we have a picture, well, we can turn this into a set of equations. So what I'm going to do is I'm going to try and copy, or let's just save it, save this PNG. And we've done our first step. Let's put this under picture. There we are. I'm just gonna trim this a little bit so that we get just the information we want. Here's our picture done. Yay! We're, a fifth through the solution. Now we have to state our assumptions and state our variables, right? We created some variables here. We created these things called VA, VB, VA prime, VB prime. All of these things, people who don't know what we're doing, they're not familiar with this, so we have to tell them, like, okay, here's what we did. So we're just gonna basically write up what we talked about. Let the train going east be train A. The west one is train B. Initially, we have VA, the initial velocity of train A. It's equal to 50 meters per second. That's what we were told up here. The train going east has that initial velocity. We also know that train B, it has a velocity. Let's be careful now. We assumed east to be positive, so then west must be negative. So this must have a negative initial velocity, negative 25 meters per second. To make that negative positive point clear, let's just assume east to be the positive direction. We also want to declare the final velocities as 0, as we kind of did in our picture. So let's declare these to be, they just get to barely the same points and then they stop. So we have VA prime is equal to VB prime, and both of them are 0. Cool. The last thing we assumed is the total, well, we're told the total distance between them at the start, st, is equal to 2500 meters. This is the distance we have here in white. We don't know what SA and SB are, so let's declare them. Let SB, this is kind of like programming, you have to declare your variables. Let SB be the distance taken for train B to stop. Let SA be the distance for train A to stop. Cool. So we have made our assumptions, we made sure to declare a positive direction, all the variables, we declared them. Now we can get to the table of equations. Remember, this is the last physics step. If you just do these 3 things correctly and you have a nice teacher, there you go. That's basically, 50 to 75% of the marks for the question that you've gotten. So here's how we approach making a table of equation. First, well, we need a table, so you can go to Insert, Table, and what I like to do is I like to have one side of the table be just the equation numbers, and then the other be the actual equations. You'll see what I mean. So let's say we have 6 equations for now. I don't know if that's how many we'll need. We can just fill in different equations, and then we can refer to them when we're solving the variables, just to be neat, just so that we can keep track of all of the different equations when we have all of these different objects and we don't know what is corresponding to what. So now we're just gonna start brainstorming. Okay, this is the brainstorming part of the problem. We just brainstorm different equations, and you don't really need to be methodological. I'll explain to you when you've stopped. But for now, let's just brainstorm. So we know, okay, from our diagram, we know that SA plus SB equals ST. We can see that, so that's the first easy equation. We need to assume that acceleration is constant. That's another thing. Assume acceleration is constant so that we can use our basic default kinematics equations. So let's see. We have v b prime. Let's focus on train B for a second. V b prime, it's going to use the basic kinematic equation, the one about, the final velocity is just, it's the initial velocity plus acceleration over time, right? So we know this acceleration, it's going to be the same for both trains because the question told us that. We don't need any subscripts here. We can basically copy the same equation, but for the other train A. There we are. So the final velocity of train A, it's the initial velocity plus the acceleration over time. Let's keep on brainstorming. We're just having fun brainstorming for now. We know that we have some equations that are like, the final velocity squared, initial velocity squared, those ones. I'm assuming you do. You've gone to Khan Academy or just learned about these in school. Oops. So this one squared minus the initial velocity squared, that's going to be equal to 2 times the acceleration times, here where the distance that we have for train B is SP. And finally, let's, we have the same thing for train A. So just change the subscripts for train A. Change the subscripts for train A here. There we are. So here's one thing that you could keep on brainstorming, right? You know that there's more kinematics equations, you could keep using them. I know that I get a sense that we can stop right now. Here's why I get that sense. What you want to do to know when is it time to stop brainstorming equations is look at how many unknowns you have. The number of variables you don't know should be equal to the number of equations you don't know. So here what I see is, okay, we don't know what SA and SB are, right? We don't know how much time SA is gonna, how long train A is gonna go before it stops, how long train B goes before it stops. We know, the final and initial velocities, but we don't know the acceleration and time. So here we have 4 unknown variables already. No new unknown variables here. We already counted acceleration and time up above. No new unknown variables here. No new unknown variables here. Okay, we have 4 unknowns and we have 5 equations, so it seems like we're good, right? We're gonna be able to solve the equations. So I didn't end up needing 6 equations. I'm just gonna delete this row. And we are done. The physics, okay? We get congratulations now, because like if you're in a university like mine, you get 75% of the marks for this question after just this. You don't need to even solve for the rest. So physics, it's not that scary. You don't even need to get a single question right the entire semester and you can still pass, so that's unique. But now we're gonna try to actually solve these equations. So now the usefulness of numbering the equation starts to come in. One thing that we might realize is, hey, we have this equation up here with SA, SB, and we have these equations down here with SA, SB. What if we try to isolate for SA and SB in these equations and then substitute them up here? That's a strategy. Let's do that. So I'm gonna be organized here. I'm just gonna comment, what I'm doing as I go along, just like in code, So isolate for SA. Let's do this. Over here, we're just gonna copy over, the left-hand side. If you note, if we divide the right-hand side and the left-hand side by 2a, on the right-hand side, we're just going to be left with SB, and that's what I want. So I'm just going to divide both sides by 2a. So here we have the left-hand side being divided by 2a. On the right-hand side, that cancels with the multiply with 2a part. So we have isolated for SB. Of course, we just copy over the same thing for, the other equation with train A. Oh, whoops. Up here, isolate for SB, isolate for SA. There we are. Copy this over and just change the subscripts, because it's the same thing, We just divided both sides of this equation by 2a. Cool. What I'm gonna do is I'm just gonna label these equations as new equations. So let's say this is equation number 6, and this is equation number 7. Cool. So we're just gonna do, as I said, plug in equation 6 and 7 into equation 1. So I'm just gonna copy over this part for SB. We have SA plus, instead of SB, I'm gonna write this part. Maybe we'll make these, whoops, maybe we'll make these square brackets just to be a little bit neater. We have ST on the side. And I'm also going to substitute this in for SA. Here we are. There we go. So now here's something interesting. I'm going to label this equation 8. Here's something interesting about this equation. VA prime, we know. VA, we know. 2A, we don't know the A. This one we know, this one we know, and this one we know. Okay, so in this equation, we have the final variable that we wanted, which was the minimum acceleration. We know that this is the minimum required, because the trains barely stop in time, right? They're almost touching nose to nose. So this is the bare minimum acceleration we need. And it's the only unknown we have in an equation. If we just isolate for the unknowns, then we find our solution. Okay, let's just do that. So isolate for the acceleration A. This looks a little bit messy, so I'm just gonna rewrite this as a fraction real quick. So let's just take the top part up here, and it's being divided by 2a. It's being divided by 2a, and then it's being added to a similar fraction, except this time for b. For b here. Note how we have the same denominator for both of these fractions. That means we can combine them into one fraction, right? So I'm just going to take this fraction here, this numerator that's being added, I'm just going to add it on top. We don't have to adjust any, anything here because the denominators are the same. And here we are. So this is saying the same thing as this equation up above. It looks kind of, messy, but we don't really care what's happening up here, right? We just care about the a. So we're going to multiply both sides by a. And that's going to give us, that's going to cancel out with the divided by a there. It's going to multiply here. That's going to almost give us the expression we want for the acceleration, except we have like this st term, so let's just get rid of that. So we're going to divide both sides by st. And there we go. This is our answer. Well, it's almost our answer. We just need to plug in, the actual expressions. So let's plug in the numerical values they gave us, and we will have our answer. So v a prime, the velocity of train A at the end, it's 0. Put in a 0. VA initial, this one was 50 meters a second. We stated that up here. Yeah? 50. VB prime, also 0, right? The final velocity of train B, it's 0. And the initial velocity of VB, remember, we were careful about this. We said it was negative because we assumed one direction to be positive. So we substitute in negative 25. In this case, you may say, why do we care? Negative 25 squared, 25 squared, it's going to work out to be the same thing. This is just to show the people that are marking in this case that you understand what's going on. In the future, you might have this not be the case, and this is a really common source of mistakes, so just be careful about that. Finally, the last thing is 2500 meters, right? That was the total distance that they gave us here. So we just need to simplify this now. 0 squared, it's 0. By the way, you can use calculators. Nothing's stopping you. 0 squared is also 0 here. 25 squared is negative 25 squared. It's positive 625. 625, here we are. 50 squared is 2500. Right? And 2 times 2500 is 5000. Cool. Let's just get rid of these zeros. They're not doing anything, so don't care here, don't care here. So negative 2500 minus 625, that's going to be 3125. Divide this by 5000. This part I can't do in my head, so what is this, Google? Okay, it's negative 3/8. No, negative 5/8. There we are. So I'm not going to confuse you, I'll just, here we are. Negative 5/8. Okay, sense check, really important, okay? Does this make sense? We wanted both trains to decelerate, so acceleration should be negative, okay? That's a point for us, that's good. Another sense check, this is really important, this is called dimensional analysis. Weird word, but all it means is, do the units make sense? Do the units make sense? Here's how we're going to check that. So dimensional analysis. If you've never seen this, this is a magic trick. So, okay, we have here a velocity, right? We have a velocity here. That means that the units that it has should be meters per second. Over here, same thing, right? You have a velocity, you should have units of meters per second. So I'm just gonna go through and do this for all of the variables we have. I'm just replacing, instead of the variable, just like what is the unit that the variable should have. So all of these velocities should be in meters per second. And on the bottom here, this meters, well, you know, it's a distance, it should be in meters. So I'm gonna put in meters here. The acceleration, it should be in meters per second squared, right? So this weird fancy expression on the left, if it's equal in units to the expression on the right, that should give us confidence. That should be like, hey, it's a little bit more likely that our answer is reasonable, as opposed to, okay, the units don't work out, I don't know what's going on. So here, I'm just gonna go through and, you know, apply all of these square terms. So if we're squaring, then we have meters squared per second squared. What happened there? Meters squared per second squared. There we are. Just gonna copy this over. Again, you take meters per second, you square it, you get meters squared per second squared. Over here too. And over here. Over here you have 2 times some quantity in meters. Well, you're still going to be left with meters. So that's that. Next up, you have all of these things. You know, you take one quantity in meters squared per second squared, subtract another quantity in meters squared per second squared, add, you know, they're all going to still be meters squared per second squared. If that seems strange to you, well, think about it like this. Well, if I have, you know, these two distances, SA plus SB is equal to ST, if these are two distances, they're both in meters, if I add meters per meters, well, I expect to get meters as the total distance, right? So addition and subtraction, that doesn't change the units. So we're gonna get rid of all this. Finally, we just have, you know, a meter being divided out, and we have meters squared here. So it's actually just going to be meters. Because of the division, it's going to cancel out the squared term. And we end up with meters squared per second squared. Well, we end up with meters per second squared. So both of the units on both sides, they were the same, right? So because of this, it seems reasonable that this is a correct answer. It has the right sign, has the right units. So this is just a magic trick to keep in mind. You can do this in your head all the time. Like, don't bother to write it all out. But just check your dimensions. We can even add that to our process because it's a good general thing. Oh, well, I deleted it. Okay, so do that in your process. Finally, in summary, the minimum acceleration, if I knew how to spell, the minimum acceleration is a equals negative 0.625 meters per second squared for both trains. Note that the acceleration for both trains is actually going to be in different directions, but that's a complication because, like, the negative direction for this train, what's going to slow it down is going to be, you know, westwards acceleration. For this train, it's going to be eastwards acceleration because, you know, you want to slow them down. So let's just write adjusting for our coordinate system, it's this for train A, and the acceleration is going to be positive for train B. I'm not a mean teacher, but if I were a mean teacher, I'd probably take marks off for that. So yeah, that's an example of why we need to make sure we state our assumption of like which direction is positive, because otherwise we would have just stopped at this answer and the teacher would have been like, no, you didn't get the right sign, and like that's unfortunate. So anyways, I'm gonna zoom out here for a second just so you can see. And we had a question, we drew a picture, we stated some assumptions, made a table of equations, solved the equations, and then wrote a summary statement, which is good because it made us reflect on the fact that one of the acceleration signs is going to be positive, one's going to be negative. So this process, it seemed long in this video. It's never going to be this long when you're doing it, every single question as you're going through all these questions. This is going to be like second nature to you. And this is really good because if you're able to do this, and by this time, the first race types, you already got 75% of the marks, you can see why the title of the series is Physics is Not Scary. Because really, if this is all you need to do, just draw a picture, state some assumptions, and make a table. Could be worse, right? It's not the hardest thing. It doesn't matter what goes on here, right? You don't need to worry about the math. After all this, you got the majority of the marks, and your teacher's gonna be really impressed because you have such an organized solution. But this is not just about school, right? Physics is about understanding the world. I find it really curiosity-inducing when I can see something, out there. Oh, this thing moved like this. What happened there? So this is just a useful skill for life. And, organize your thought process and it will be easier to think. So with that being said, here is the easiest question of this series, and more importantly, the process. Keep this in mind because we're going to keep using this process again and again, and I'll stop mentioning, hey, we're doing that process again.